Okay, so this is our last video that we're going to do for today's lesson, and this is going to be similar to what you're going to have in your homework here. So what you're given here is you're given an equation and you want to prove this statement, right? So the whole idea is we want to show that a statement is true. We want to show that this statement is true. How are we going to do that? Well, we're going to use a logical argument. We're going to do a chain of deductive reasoning, and we're going to start with this, and we're going to use steps where we justify each step with either a definition, a postulate, a theorem, or a property. Now in this case, they're pretty much all going to be properties. When we get into geometric proofs, when we start talking geometry, we're going to be using like postulates that we've kind of written down, like Euclid's 5 postulates. We're going to be using definitions that we've written down, like angle and segment and perpendicular bisector and things like that. We're going to be using theorems eventually. We don't have any yet. And we'll also be using some of these properties of equality and also properties of congruence, which we'll talk about soon. So right now, we're just going to try to prove this. So to do a proof, there's multiple ways of doing a proof. What we're going to do, and the structure we're going to use for the first little bit here, is a 2-column proof. This is a really nice way of organizing your arguments, and each line is its own argument. And so what you're going to have is you're going to have a statement, something that you say, this is true. You're going to say, I say this is true. And then you're also going to have a justification where you say, I think it's true because, or the reason it's true is because of this property. So these are justifications. But you also might see this as reasons. Some people call these reasons. Just depends on where you're at. Okay? The first statement in a 2-column proof is always the given statement. It's just the one they start you out with, right? We're going to have statements like if-then statements or conditional statements. If two angles are supplementary, then they add to 180 degrees or something like that. But right now, this is just a mathematical or algebraic statement with an equal sign, right? So this stuff equals this stuff. This expression equals this number. So that's what we start with. Okay, and the justification for that first statement always is just given. This is what they gave us. This is what the problem has given us to work with. Okay, so we're always going to start there. Now our last statement in this proof is going to be this guy. This will be our last statement. Whatever statement you're trying to prove, that's going to go last down here. And we're going to try to kind of build it in between. So the next statement that I would do, well, let's think through that. What would you do here? What would you do to this equation first? First thing you want to do. There's more than one way of solving this, but if it were me, I would distribute that -5 to get rid of those parentheses. Okay? So the next step I'm going to write here, and we're not really going to, we're kind of showing our work. We don't show all the little pieces of our work. We just write the next statement and say what happened, right? So we have -n. Now we're going to distribute this -5. So -5 times 1 is -5. -5 times 3n is -15n. And that's going to equal 91. Okay? Great. Now what do we use there? What's the justification for saying that? If you were talking to somebody and they said, how did you get from here to here? Explain that to me. You would say, oh, I just distributed, right? So the property that we're using, remember we can say it's a definition or postulate or theorem or property. Here we're just going to be basically using properties of equality. So actually that's a property of multiplication, excuse me. And that's the distribution property of multiplication. So we're going to go distribution. We'll use a little bit of shorthand here. Property of multiplication. Okay, remember that's a property of multiplication, not a property of equality, but here we go. Okay? Now the next thing we might want to do is to combine like terms, right? So we want to combine these like terms. So you could say that this is going to be -16n. There's a couple different reasons why you can say that, and it kind of depends on how thorough you want to be. Just for the sake of being really thorough here, let's rearrange it first. Okay, what did I do? I rearranged it so the ends were next to each other. What property is that? That's the commutative property of addition, right? I can just, this is all, it looks like these are subtractions, but this is like -n plus -5n plus -15n, so I can commute it around here. So if you wanted, now you don't have to do that step on your homework if you don't want to, but if you did do that step, then you would call this the commutative property commutative property of addition. Okay? Again, just kind of a shorthand here, which you're welcome to do on your homework as long as it's clear what property you're talking about. If you just say, you know, mult, I don't know if you're talking about the multiplication property of equality or the distribution property of multiplication. So you can't just say multiply, divide, add, subtract. We're not talking about operations, we're talking about properties. So you can't just say I multiplied, I divided, I added. You have to say a property, right? We're talking about an established property. So the property of multiplication, the addition property of equality, or something like that, okay? So be clear here. Don't just say, I divided. These are all going to be properties. Okay, next step is we'd actually combine these like terms. So when we do that, when we actually say, these things are going to combine to give me negative 16n, what we're really doing is we're replacing this with what it's equal to, right? We know like negative n minus negative 15n is negative 16n. Since we already know that those are equal, this step is really a substitution step. And it's a property of equality, right? So substitution. Now be careful with sub because there's a subtraction property. So I'm going to say subprop because I don't know if you're talking about the subtraction property of equality or the substitution property of equality. And you need to be kind of specific here. So as long as we all understand each other, we're going to say that's substitution, sorry. We're going to say substitution, right? That's not subtraction. Substitution prop of equality. Okay, so you don't necessarily have to write all the words out, but again, it needs to be clear what property you're referring to because it needs to be some established property. Okay. All right, where would we go from here? Well, the next step would be to minus 5 from both sides, right? So if we're solving this problem, we would actually write, or sorry, we're going to add 5 to both sides, excuse me. Add 5, right, cross it out, okay? We don't do that in a proof because this is not, we're kind of showing our work, but really what we're doing is we're making statements. We're not scratching stuff out and working it out, we're just making statements. If we were to add 5 to both sides though, we'd get rid of this guy, that would cancel out, and we get a 96 over here. So the next statement then is negative 16n equals 96. And the reason for that is we added 5 to both sides, so the addition property of equality. Okay, saying add right there is not enough. If you say add prop of equality, cool, I know what you're talking about. But we're talking about a property, not an operation. Not what did you do, but how did you know you could do that, or why is that equal? This is not saying what you did, this is justifying what you did with a definition, property, theorem, or postulate. So we need to use a property here. Okay, next thing, or the last thing here, is to divide both sides by negative 16. Because this is a negative 16 times n. We're trying to undo operations on n. Now again, if we were solving this problem, we would normally do something like this and cross it out and say n equals. But we don't show that part in the proof. Okay. We just show the next line. Okay. So if the next line of the proof is, divide both sides, what we're going to get here is n is equal to negative 6. Now you can double check. You can go actually do 96 divided by negative 16 and make sure it's negative 6. It is, but that's kind of what you get. And how do we do that? We did the the division property of equality. Okay? Now notice the last statement is the statement we're trying to prove, so this is where we end. We say, okay, we're done. And it's pretty common to, when you're done with the proof, to put a little square at the end to say finished, or like it's complete. We've gotten where we wanted to go. We've justified every step along the way. This is a pretty bulletproof argument. Nobody could really argue with this because you've justified it at every step. It's kind of like being a lawyer and saying, ladies and gentlemen of the jury, it is my intention to prove to you that n equals negative 6 from this mess. Now, first, you'll notice that this is what I'm given. Secondly, because of this property, I'm allowed to do this, and so on and so on and so on. Okay, and then you get to your n, and you're like, therefore, ladies and gentlemen of the jury, I submit to you that n equals -6. You must convict. And then the jury's like, oh my gosh, that's solid reasoning. I can't argue with that at all. He's guilty. So that's kind of what's going on here. One other thing I wanted to show you really quick that you'll sometimes see. Let's say, now this isn't true in this guy, but just for the sake of argument, let's say we got down to the very, very end here, or close to the very end, and we got something like this. -6 equals n, and it was like reversed, right? Well, this statement and this statement aren't exactly the same. We know that they're equivalent because of the symmetric property of equality, but we haven't stated what we wanted to state just yet. So if you get something like this, you need to go one step further and you need to actually switch them around, and your justification for that step would be the symmetric property of equality, because you're just switching them. So it's pretty obvious that that's the case, but doing a proof is not about assuming the other person knows what you're talking about, or it's not about like, you know what I mean, et cetera, et cetera, et cetera. It's about creating a bulletproof, airtight case where you're like, you cannot argue with me. This is exactly what it's supposed to be. So although sometimes these steps seem kind of like, well, you know what I mean, right? We want to do this very rigorously and very precisely so that nobody can come punch holes in our argument later. Nobody can say, well, this isn't what you wanted to prove. Like, I'm not buying it. You're like, you know what I mean. There's no you know what I mean when it comes to proofs. It's just like, nope, this is why. And then it's like, okay. So you almost pretend like the person you're talking to is like not smart. Not because you don't think they're smart, but because you're, again, you just want to prove everything rigorously. So this is kind of what you're going to do on your homework. Now, of course, we didn't really have to do this last step because when we solved this, we got n equals -6, and that's what we wanted, the order that we wanted, so we're good. But you might see it reversed on your homework. So check out that homework, go in there, solve the equations, right? You should know how to do that. This is familiar. This is the kind of stuff that we want to add in, and this is going to be a good practice for next week or the next couple days when we actually start doing proofs with angles and proofs with segments. So thanks for tuning in. See you guys soon.